Water boils when it is heated, but water can also boil at room temperature. In this glass venturi, water is flowing from left to right. According to Bernoulli's integral, where the velocity is increased, the pressure is decreased. When we increase the flow rate, the water in the throat, where the pressure is lowest, begins to boil. Small bubbles are formed. These are cavities filled with cold steam and other gases diffused from the liquid. The noise is generated by the collapse of these bubbles as they move into the higher pressure in the diffuser. Water is flowing past this propeller model at constant speed and pressure. Let's increase the RPM of the propeller continuously. Bubbles form in the regions of lowest pressure in the flow. To visualize the flow more clearly, we look at it under stroboscopic lighting, so that to the eye, the rotation appears almost stopped. About 100 years ago, when propellers began to replace paddle wheels on ships, it was discovered that such cavities produce a great waste of power. These cavities on the propeller, the bubbles in the beaker, and in the venturi throat are all examples of cavitation. Generally, we refer to cavitation as the process of boiling in a liquid as a result of pressure reduction, rather than by external heat addition. However, the basic physical and thermodynamic processes are the same in both cases. In this film, we will see the various forms of cavitation, illustrate some of the consequences of cavitation in engineering applications, and examine the physical factors involved in the process of inception and development of cavitating flows. First, let's look at some different types of cavitation. We will work in this circulating water channel. Here we can vary water speed and temperature and absolute pressure independently of each other. This hydrofoil is set at an angle of attack to lift upward. With this thick, symmetrical hydrofoil, we can illustrate a number of effects on a single model. The ambient pressure is well below atmospheric and held constant. The flow speed is being increased at a uniform rate. Air bubbles have been introduced to help visualize the motion. Cavitation occurs first at the intersection of the hydrofoil and the strut. This happens because the presence of the strut causes a greater pressure reduction at this intersection than elsewhere on the foil. But we will confine our attention to the foil section away from the influence of the strut. At low speed, cavitation on the foil itself first occurs in the low-pressure core of the laminar boundary layer separation region associated with low Reynolds number. At higher speed, and thus larger Reynolds number, the appearance of the cavitational flow changes. Transition from laminar to turbulent boundary layer has occurred. Laminar separation has been suppressed, and cavitation now begins near the minimum pressure point, close to the leading edge. We have been looking at the cavitation under incandescent lighting. Under stroboscopic lighting, we see that the cavitating region is again made up of individual bubbles. The apparent dancing is only a consequence of the strobe lighting. Actually, each flash of the strobe reveals different bubbles in different locations as they travel downstream. With high-speed photography, we can follow the history of the same bubble as it is swept downstream. Each bubble grows as long as it is in the low-pressure region of the foil. The bubbles collapse when they enter the higher pressure region near the trailing edge. Individual bubble cavitation is characteristic of forms with gentle pressure gradients, such as those on this foil with a well-rounded leading edge. When the leading edge is sharp, however, cavitation begins at this edge. This type of cavitation maintains itself as a continuous vapor-filled cavity, rather than a mass of small individual bubbles. Its size depends on the angle of attack, the ambient pressure, and the flow speed. The cavity grows when the angle of attack is increased. It also grows when the ambient pressure is reduced. We are lowering the pressure by dropping the water level above the foil by means of an upstream sluice gate. The cavity also grows when the water speed is increased. When the cavitating region extends beyond the trailing edge of the hydrofoil, we call the flow a supercavitating flow. The supercavitating, sharp-edged foil is a type used on very high-speed hydrofoil boats, such as this 80-knot boat. Hydrofoils designed for non-cavitating or subcavitating operation are used on hydrofoil boats at speeds below about 50 knots. Let's look at the propeller model again. At this point, we want to emphasize the role of the ambient pressure. The pressure is low and the propeller RPM is constant. Notice the cavitation on the blade faces as well as in the tip vortices. The pressure is now being increased by raising the pressure of the gas above the water surface. The cavitation is reduced, and now it is almost suppressed. Incidentally, this procedure simulates the behavior of a cavitating submarine propeller as the submarine dives from a level near the ocean's surface. This model is typical of a propellation. Here is a propeller designed to perform well at very high speed, where cavitation is unavoidable. This type of propeller operates under supercavitating conditions. Under stroboscopic lighting, we can see that the cavities spring from the leading edge and envelop the entire blade, as in the case of our supercavitating hydrofoil. Cavitation may also occur in hydraulic machinery, such as pumps and turbines. Here is cavitation on the blades of an inducer pump model seen with strobe lighting. Cavitation can also occur in turbulent shear flows because of the local pressure reductions in intense turbulent eddies. For example, let's look at the flow behind this circular disc. As the flow speed is increased, the pressure fluctuations in the zone of high turbulent shear lead to cavitation. With further increase in speed, the entire wake appears to be filled with vapor bubbles. Eventually, the flow becomes a true cavity flow, as distinguished from a cavitating turbulent wake. With high-speed photography, we can see more of the details of this complex flow. The flow at the end of the cavity re-enters and moves upstream. This re-entrant flow is illustrated more clearly in the cavity trailing our supercavitating hydrofoil. Re-entrant flow is characteristic of such cavity flows. The momentum flux in the reentrant jet is equal to the pressure drag of the body. The jet kinetic energy is dissipated. Another type of cavity flow occurs when a missile enters water at high speed. In this sequence, a steel ball is shot into a tank of water. Here, the camera is turned so that the water surface appears to be vertical and the missile to travel horizontally. The cavity follows the missile into the water and eventually closes off, producing reentrant jets which are seen here in slow motion. Initially, the gas within the cavity attached to the missile is air rather than vapor. Progressively, the air is left behind, and if the motion persists long enough, the cavity content will be vapor primarily. Still another example of cavitation occurs in the type of bubble chamber used for studies of high-energy nuclear particles. In this photograph, a positron-electron pair has produced a track of bubbles in liquid hydrogen, which is at a pressure below the boiling point and is therefore unstable. We have seen that cavitation can take several forms: small transient bubbles, large, more or less steady cavities, non-stationary cavities, and often a mixture of these types. Let's turn now to an examination of some of the effects associated with cavitation and cavitating flows. What happens to a machine when it begins to cavitate, and how does performance vary with increasing extent of cavitation? Since hydrofoil sections make up so many different types of machines, pumps, turbines, propellers, propeller shaft struts, mixers, we can illustrate what happens to all such machines by studying the forces on the hydrofoil section itself. We have suspended the first hydrofoil model from force gauges, which show us lift and drag on these scales. The flow speed is constant, and the gauges register the corresponding lift and drag. The ambient pressure is set at a level well above that at which cavitation can occur. We are going to induce cavitation by decreasing the ambient pressure in the test section, keeping the speed constant. At first, there is no appreciable change in either force. As cavitation develops, lift decreases and drag rises. You can see from the force balances that the flow is quite unsteady. When we lower the pressure further and allow cavitation to spread, the lift decreases further and the drag continues to rise. We can get an idea of what has happened by examining the pressure distribution on a hydrofoil section. This curve represents the pressure on the upper surface, and this one, the pressure on the lower surface, before cavitation begins. The lift is proportional to the difference in the areas under the two curves. As the ambient pressure decreases by a certain amount, the pressures on the upper and lower surface decrease by exactly the same amount, at least until the upper surface begins to cavitate. At this point, the upper surface pressure can no longer decrease below the cavity pressure, which is near the vapor pressure. Since the pressure on the lower surface does decrease, the lift drops. Actually, as cavitation develops, the shape of the pressure distribution changes somewhat. The resultant pressure distribution is such as to cause an increase in drag. Thus, hydrofoils, and for the same reasons, many hydraulic machines, which are designed for efficient subcavitating operation, lose efficiency when cavitating. Where cavitation is unavoidable,